directly from an input port into something, or we can move things from an output port into something. So what I've got is I've got my PLC running up here, and we'll wire up the outputs too in a second, or I'll wire them up. But this is a very simple program. So what I'm doing is I'm taking a source, which is in this situation, it's going to be a constant. Okay. Just a little thing, right? Now, the move instruction operates with words, so we can't split that up. So anything we deal, we got to deal with a word. Well, what I'm doing here, as soon as it gets up, is I'm taking my source, and where am I putting it at? I'm putting it in output word 0. Everybody okay? Makes sense? How do I know it's a word? Because that little period that everybody had problems with. So this is going to be, it's not slot 0, it's word 0, right? You understand? Because we don't have slots on this. I'm sorry, the word group 0, or and then it would be word 0, right? Everybody understand? Did I say that right? Okay. So what I'm going to do is I want to, on this PLC, I've got 6 outputs on this. But actually we could store in the whole port. It don't care, but so we can look and see what's going on our outputs, even though this PLC doesn't have one. So right now, this output is off, this output is on, this output is off, this is on, this is off, this is on. So let's say I wanted to turn every other one off on. Well, notice what I would have to do. I would have to come up here, and I would have to write out that binary code, and I would have to convert it to decimal before I could enter that in there. Well, that's the pit. So I'd have to figure out the decimal equivalent of the binary number. Well, guess what, guys? We can enter binary directly. We can enter hexadecimal correctly. By default, if you enter any number, it considers it to be decimal. So what you have to do is you have to tell these things if you're dealing with binary. That makes sense? So if I wanted to turn every other port on, what I'm going to do is I'm going to come up here. I'm going to have to take it offline because we're using a constant here. So we can't. So what's the difference between a constant and a variable? Variable we can change without changing the program. A constant, we have to change the program to change the number. So what I'm going to do is I'm going to come up here and I say we want to turn off every one of them. I'm going to come up here and enter in binary. I'm going to say 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0. Okay. Well, what I have to do is I have to tell this thing this is not what? Decimal, because right now you would think this was an extremely large decimal number. So I have to tell it's binary. So I'm going to just come up here and end my number with can y'all see what I put there? A B. And then when I hit enter, it's going to convert that to decimal for me. Of course, it thinks it's a negative number because the most significant bit is set, but it don't make any difference. Because it's still the binary number. And then I'm going to come up here and download it. And of course, now when I move it, output port is that instead. You can hear my outputs turn on up here. Well, what we'll do is let's look at the outputs, and then I'll come up here and I'm sorry, the switch is already made. I should have turned the switch off. Sorry. But what did it do? 1 0 1 0 1 0 1 0 1 0 1 0 0. See? So if I wanted to turn on outputs with a move instruction, instead of me trying to write down the binary code and then convert it to decimal so I could enter it in the move instruction, I could put 1s and 0s instead of and end it with a what? A B. Or I could enter in hexadecimal. What do you think we'll do if we enter a hex number? No, it's going to convert it to decimal. That's all it knows. But all that sucker right there deals with is binary anyway. It's up to your compiler or your translator what it does with the number, not the PLC. The PLC sees that 10101010. It does not see minus 2000, whatever it is, right? You understand? It's up to the translator that translates this over. So I could come up here and enter A, and that's 16 bits, but I'm going to enter it with a what? An H. Now the translator is going to say, okay, he entered it in hex, so I'm going to take this hex number and convert it over to decimal and display it in decimal. It's never converting, right? You understand? It's displaying it in decimal. Okay. And then, of course, it's going to be a minus number anyway. Y'all understand minus, right? So a binary has got to be able to represent signed numbers. So the way it does that is if we're dealing with signed numbers, if this bit 15 is set, if it's 1, it considers the number to be negative. If it's a 0, it considers the number to be what? Positive. And we're not going to tell you how it comes up with 21,000. It's a complicated process. But if this thing ever sees, if we're using an instruction that deals with signed numbers, which this guy does, if bit 15 is set, it assumes it's what? Negative. If bit 15 is 0, it considers it to be positive. And then after that, it uses a technique called two's complement. We won't get into that because it's going to be transparent to us anyway. So let's turn my switch off. And let's don't do, what do y'all want to do? Let's do a strange thing. Let's say I want to come up with, and we'll do it in hex. So let's say we want to turn this one on. This looks like it's yellow. Help me see that. Really like this thing. Well, let me bring up a PowerPoint and do it on there. Because that way it'll be recorded. The other way it wouldn't be recorded. So how do you want to turn these things on? Well, first of all, I would figure out how I wanted to turn them on. And I could type in with binary, but I'd be typing in 16 bits, right? You understand? If I do it in hexadecimal, I'm only typing in what? 4 digits. So I would come up with how I want to turn these things on. Let's go 110010111011101101. Is that 16 bits? 1, 2, 3, 4, 1, 2, 3, 4. Yeah, and then we'll put a 0 at that. Well, what I would do is I would convert this to hex. So this would be a what? 6. This would be a 2. This would be a 6. I'm sorry. This would be a D. I didn't see the other one. I see my dashes up there, right? So this would be a D, and this would be a D. 62DD. Well, I've come up with my code now, right? You understand? So what I would do is I would come into RSLogix now, and I would enter what? 62DD. But I'm going to say what? H. Now it's a positive. It's going to say it's positive because the 15th bit wasn't set, right? I'm going to enter that. And then what I'm going to do now is I'm going to download it. And then we'll look at our outputs. And the switch is not closed. Okay. It says it is because I still hadn't gone online. Okay. So we'll bring up the output. And so as soon as I just touch that switch, what did it do? It came up the way we decided we want to do it. I could also split it into octal. So how would I tell it was an octal number? And we do O. So if I don't want to use decimal, if I want to enter information in binary, I just make sure you put 1s and 0s or you'll get an error, right? And I end the number with a what? A B. If I want to enter it in hexadecimal, I enter my hex number and I enter it with a what? A H. no longer than 4 digits, right? Because we're dealing with words. If I wanted to enter it in octal, I would enter it with a what? Oh. So that's where these bases come into play, especially when we're dealing with getting information and sending it to an output port directly without using output to energize instructions. So you can set up those output ports any way you want to, right? You understand, without, and good gracious guys, that would save tons of codes. Instead of me going on turning on a lot of relays or turning on a lot of outputs just to get the outputs in a certain state, right? You understand? What could you do? You could set them in that state with a what? With a move instruction. One move instruction. Cool, right? Very powerful. The move instruction. But your source could be coming from where? We could bring our source from switches, right? I'm going to do that. Now we got 10 inputs on here. We could bring them from what we call thumb wheel switches, but what happened to my program? I'm gonna download it, upload it from the okay. What? I know that. Okay. So what we'll do is we'll come up here and take my source and we'll bring it in from input 0.0, which is on the trainer. So this means we're loading in a whole word, right? You understand? There's not a whole word out there, but we'll show you later on how to get rid of the bits on your input port that's not being used. Clears up. See, all my switches are off. And we'll download it. So we could load a timer. We could load the preset register on a timer with what? With switches. I mean, they could be up there. So what do we want to do? I'll just come over and flip some switches on. Okay. And then what I'll do is I'll have to do, it should be changing instantly because I got it. Well, that's good anyway. So we got it loading all the time. Right. Oops. That was one of my switches. Let's see what's going on. So I'm taking the input switches and I'm moving directly to an output port. That's as far as this one goes. It's only got 10 inputs, 0 to 9. So you could use a move instruction to get information from input devices, right? You understand? And then take them to an output port if you wanted to, or take them into a storage location, or do math with them. There are all types of options available with this move instruction. Very powerful instruction. So every PLC that I've ever programmed has one of these guys. A move instruction. Are we okay? Yes, no? Okay, so let's go back and review counters for RS Logic. So tell me everything you know about counters. So RS Logic 500 supports 2 types of counters. What? They support what? Count up and count down. And they're single input counters, which means what? So Siemens uses 2 input counters. And RS Logic 500 uses single input counter. So we use the enable and the count is the same thing, right? You understand that? So we use single input timers too, right? And we have the reset instruction. What do we do with the reset instruction? We have one timer that requires it. What's the one timer that requires it? Yeah, the retention timer, right? And then we have both counters required. And so both our counters, whether it's an up counter or a down counter, requires it. This PLC, the RS Logic 500 does not support an up-down counter. I don't know about RS Logic 5000. I need to do some research on that. So they're similar to timer company. We use the block. We don't use the coil method. I'll try to hook up the Siemens 1200 up and let you see. Siemens supports both types. So whichever type you're used to using on the Siemens, you can either use the coil method or you can use the block method. RS Logic 500 only supports the block method, which is basically came into play when they came up with the function block programming. So Allen-Bradley 500 series program logic controller uses one input, so we use one input for what? Count and enable, right? Understand that. We can address these things once we decide a data file. So by default, or we got half K of memory set up for, or that's actually for data file 5. It's set up, but we can, if you're on the 1000, that fixed PLC, guys, that's all you got. This guy right here, the hybrid PLC, you got this available to you. I mean, if you run out of 5s, or you want to use, or you don't want to use 5, right? I had one guy that said he never uses the defaults because he likes to tell if he wrote the program or somebody else did. So he uses these data files up in here. First of all, 5 you can't use anything but for counters, right? Understand? These you can use for anything. So what that means is that you're responsible for that. So if you use 9 for counters, then you cannot use 9 for timers, right? You understand that? And it's up to you to keep up with the data files that you use that's outside of the range. So we'll use 5, okay, but I want you to understand we can, and I think I showed you that on timers. I set up a timer up in data file 9 the other day. But once we set up a data file, we can have up to 256 from 0 to 255 counters inside the data file, right? Everybody okay? If you have more than that, then you would have to use one of these 9 to 255 if it's supported by the PLC that you have. I thought I came back and reworded all it. The book, guys, does not use the right terminology. There is not a register. These are not registers. These are words. We have counter words. We have 3 counter words, and I thought I corrected all these. If you look at the data book that goes to the instruction set for the 1100 PLC or any Allen-Bradley PLC, you will never see the word accumulator register. A register is inside the microprocessor. These guys are not inside the microprocessors. They're out in the RAM memory of the PLC. So technically, these are not registers. Technically, these are work. So the accumulator occupies a complete work. So every counter that you set up takes 3 words in it. 3 words in it. One of the words would be for your accumulator. The other one would be for your what? What registers are inside the counter? Or not, what words are part of the counter? We know we got the accumulator. What's the other one? Preset register. It's a 16-bit register. Or word. It's a word. What else do we have? Now, that's not a register. That's a good point, but it's not a register. It's just something we put into the instruction. We tell it how to multiply. We call it the time base. And why they came up with that, guys, I don't know. It's just what we have what we call the status word. It shows us the status of your counter, right? You understand? So we have a accumulator counter, and we have, here we go, I did change it. I just didn't change it back there. So we have a preset word, and we address it C. Then if we don't use one outside of 5, then we'd substitute that for whatever data file we use, right? To understand that. Then we put a dot. Why do we put a dot? Because it's a word, right? Right? And then we would type in PRE. So you don't need to know the address of the preset register. Your translator knows where it's at for you. That makes sense? Well, this is the way we could directly address the preset register. So we could load it with anything we wanted to. So we can put a constant in there, right? We can put a preset constant in there, or we can address it. So I could take an input port and I could send it to this register with the move instruction, right? Don't understand that? Pretty good. Then we have the accumulator word. It's addressed the same way, but instead of me having to actually know the address, what address it's at, we can address it through what? Word. Yeah, ACC, though. That's what I was looking for. Okay. And then we have the status word. It holds the flag bits that are used by the programmer to keep track of the operations of the counter. And what you can do is you can address it with a name, or you can address it by the bit. Let me go ahead and let me show y'all to give y'all an example. And these are all available to you guys, and this guy tells you a lot more information than what the book actually tells you. So on Blackboard, I'll get it from here because it's a lot faster. You got PLC manuals up there, and all these manuals are free. So I think I was telling y'all the other day that when you buy the PLC, they really don't come with anything. But they know everybody now has access to what? To the internet, and they would go up there and download these. So every one of these were downloaded from the internet, and all these should be available. PLC manuals and Allen Bradley, and then the 1100 instruction set. So these are all the instructions that the 1100 handles. And it also shows you how to wire it. We're down here in timers and counters, right? Okay. And then what I'm going to do is I'm going to close this, make it bigger so we can look at it. This shows us where we need to go to. It's got to look at these different things. So we're down at counters. And this tells us basically how long it takes to execute the instruction. So if I was really an engineer and I needed to know all this kind of stuff, then I would be able to calculate my scan time. This is not in the book. So this guy takes 2.28 microseconds if it's what? If it's true, or 2.5 or 15 microseconds if it's false. Counting up or counting down. But I'm looking for the registers. So here's the actual bits. So my underflow is bit what? 11 status register. my count down is what? 13. But we don't need to know that because it allows us to address it by what? By name. So they've given these names by transit. And then my countdown bit is 14. This is how many ways we can address it. We'll look at those later on. So one of the things we're going to learn is how we can address those operands. So this guy can address operands 3 different ways. Immediate, it means it's part of the instruction. So constants would be what we call immediate address. That where I give it an address, where I say input, so this is direct address, and we'll talk about that later. So if I put an address of a data file in there, like an output file, that's direct. So direct means you're giving directions to where it's at, right? Immediate means it's what? It's part of the instruction. These are called addressing modes. They pull this up from that. This tells us what type of data files we can have. And this is the 3 words that make up every counter that you set up takes 3 words a minute. Word 2 is the what? This is the accumulator. Word 1 is the preset. And word 0 is the status. So we say we have 256 counters available, but it actually occupies 3 times that, right? You understand that? Now, luckily, we don't really have to know this because we can address these different registers by using what? .acc, .pre, but I just wanted to show y'all basically what's going on. So there's a lot more information inside the actual books that come with the PLC, and this book has the ability to use. And they don't call them registers; they call them what? Words. Because technically, a register is inside the microprocessor. A register is not inside. A register inside the microprocessor is actually the memory in the processor where it holds the information while it's actually being processed. So we have several registers inside there that we're not going to get into. And it all depends on the different types of microprocessors. And this gives us a count up and count down. So we got 2, and we got the same thing with timers. So timers are basically like this. So it's going to take up 3 words for every timer that you put in. It's going to be set up basically the same because basically timers are almost the same, right? You understand that? Except that the status bits are different. So this is available up there, and we'll be looking at that several times in here to get a better feel of what these instructions do, because the book is good as far as what it does, but sometimes it don't give us enough information to figure out what's going on. Like using the term registers when in fact these are not registers, these are just words out of memory somewhere, right? Oh, in fact, there it is. So where did I get this from? This is not in y'all's book, I don't think. Where did I get that from? Manual. Yeah, I read out of the manual. These are the 1100 counters. And also the 1000 counters are just exactly the same. The big difference between the 1000 and the 1100, one big difference is we're stuck with what we got, right? So C5 is counted. C4 is time. I mean, T4, gather word 4 is time. And you cannot choose those extra memory inside the PLC like we can with 1100. So 1100 is that. But I think we have enough 1100 down there, by the way, for everybody to use one of those. So we're going to move on to those because they'll do everything that we want to do in the class. So we have the 2 flags. We have the count. We very seldom use these. These are the enable flags. So this will tell us when so these guys here they would be true every time you have count, right? You understand? I don't know why we would use these because we could get it from the device that actually is bringing in the count. So we could get this from there. We do use the done bit a lot. This is probably the most used bit right there is the done bit, right? Which indicates when the thing is what? Yeah. Overflow indicates when it exceeds signed numbers. So overflow, I didn't correct that either. Y'all see what's wrong? So I copied these over from the last. And that's my fault, guys. That's not the book's fault. So we have access to 14 bits. So we get two to the 15th. I'm sorry, we get access to 15 bits. We don't get access to the 16. So we would get up to 2. We would get up to 2 to the 15th power, right? I'm sorry, 2 to the 14th power, because remember we start with 0. 2 to the 14,000 is 32,768. Well, how do we identify positive and negative numbers when we deal with positive and negative numbers? How do we know it's positive? How does the PLC know it's positive? Or how does the computer, every computer I've ever dealt with deals with this. Because I have the ability to deal with negative numbers on this computer right here. So it's got to be able to handle negative numbers using binary. Well, binary, there's no plus symbol and there's no minus symbol, right? All I've got is ones and zeros. That's all I've got. So how do we indicate, if we're dealing with signed numbers, how do we indicate a signed number? Well, the most significant bit, right? You understand? The most significant bit becomes the what? The signed bit. If that bit is set, if it's a 1, then these guys assume it's what? Negative. If it's a 0, it assumes it's positive. With 16 bits, I have 65,536 combinations. If I divide that by 2, it comes up and gives me 32,768. Well, why don't we have 32,767 positive combinations? 0 takes up one of your positive combinations. And 0 has no sign. There is no such thing as a negative 0, right? You understand? Even though some of y'all might think that. So that means if we're dealing with 16 bits, then this is what we got. We got 32,767 positive combinations. We got 32,768 combinations. Your counters keep up with the number. If you go past that, and we showed y'all this the other night, right? If we go past that, then what does it do? If you're counting positive and you go past that limit right there, then what's it going to do? It's going to switch over to negative. Even though it's not negative, it's what? Positive. And it's going to keep counting, but it's going to show you've got negative values, and you need to do what? You need to compensate for that, right? Yeah. Well, we could do that. We could cascade counters, right? You understand? We could cascade counters, and if the overflow bit ever set, then we could switch over to the next one, or we could limit our counts, right? So we could do tens, we could do hundreds, we could do tens, we could do thousands. We could have 3 counters, and then that way they would do what? Every time it got done, we would go over there and we'd enable the next one. And then we'd reset the counter, and then your units would start counting from 0 to 10. And that way you'd be counting in decimal, right? You understand? So we'd have to compensate for that. By the way, the 1100 supports what they call a long word, which is 32 bits, right? So we can get big numbers out of this puppy, but we'd have to specify long words. Y'all understand this? So up, down, a down counter starts at here and counts down. And then if you exceed the signed numbers, you get an underflow, right? An up counter would do what? Count up to 30,767, and then you get an overflow, but it was with signs. So what you need to do, if you're going to count over that, if you know you're going to count over that, you need to do what? That's something you have to take care of with your program, because what's the counter going to do? So when the counter hits its preset, what's it going to do? No, it's not. It's going to keep counting until you reset it, right? You understand that? And that's up to the programmer. That's not up to the counter. The counter's never going to lose counts, right? You understand that? So this is an up counter. So here's our enable, and it's not only our enable, it's also our what? Count, right? You understand that? This is the address for the counter, C50. It could actually go up, if I'm using C5, it could go all the way up to what? 255, right? If I've got the right PLC and I need more counters, then I could jump up into 9, data file 9, right? You understand? Why data file 9? Now that's where your free memory's at. So we have to use this. And we have to remember, how do we see that? Oops, wrong thing, Rick. So in our project trees, these are the data files that are reserved. So 0 is reserved for what? Output. 1 is reserved for inputs. 2 is reserved for data. That we'll use. It's a data file, but we have some instructions that don't have an internal status register built into the instruction itself. Like our rotates and our shifts and stuff like that. Then we have what? This is 3 is for what? We call that bit files. These are for bit files. This is where we're going to address these things individually. You can. So normally our internal contacts are right here, right? Like normal. 4, data file 4 is reserved for timers. Data 5 is reserved for counters. 6 is reserved for control register, right? So we'll use this semester too. 7 is for integer numbers. 8 is for floating point. So what's the difference between integer numbers and floating point numbers? We're going to deal with those this time. What is an integer? So counters use integers. Whole number without a decimal point. Without a decimal point. There's no fractional portion of an integer. It can be signed, so we're dealing with signed integers. Counters use signed integers. Timers can use floating point numbers because we can put a watt in it if we choose a small multiplier. We can put a fraction in there, right? Now, I think it does the multiplication on the fly. I think it's integers too, because we enter the number in integers, right? What's a floating point number? It's where the number can float, right? The decimal can float. Floating point numbers uses scientific notation. So as soon as we jump into scientific notation, what do we lose? Accuracy. We lose accuracy. Well, I don't know how many. I'll have to go back and see how many digits it goes. I think it's 2 to the 24th. I think 2 to the 24th holds the digits of the number. Then the other bits are used to hold the power, how many powers you can have. That's defined by the PLC too. How many exponents you can have, excuse me. But that's a big number. 2 to the 24th is a big number, right? So it uses a double word or a long word for floating point numbers. So if I'm going to deal with numbers that's got fractions in it, then I've got to deal with what? A floating point number. So later on we're going to get into math. And of course division, we're going to do division. And division we're going to have to use what? Floating point. Because there's a lot of numbers, we end up with what? Fractions. So we're going to deal with math operations this semester. We'll have to figure out, the book only covers the basic math operations, which would be what? Add, subtract, multiply, and divide. That's the only one the books cover. Some of them have trig functions. I don't know if 1100 has trig functions or not. A lot of PLCs don't have it. If you need trig functions, you need to make sure it's got that. Some of them use other types of things that you can get into. Yes, math. It is. So what we have problems with though is this down counter, right? So up counters are pretty straightforward. We load the preset, and then it starts counting from the preset. Usually our accumulator starts at 0, but we can address the accumulator so we can put anything in there we want to, right? So an up counter starts with 0. So let's set up a new. I might have one out there already. Let's do it. Let's do it from scratch. So how do we do that? Yeah, we go to new, right? Here. Okay, let's go offline. Yeah. No, we don't do that. It's not going to do that. Okay, so once we set up a new program, first thing we got to do is what? We got to configure the CPU. What's nice about the MicroLogix, these are the model numbers over here that's on the side, but also you've got names, and once you learn the name, so we got the 1100B, which would be this guy right here, right? And then we got two options. We could do what? We can come up here and use this palette here, or we could use this tabs, or we can do what? We can bring back our instruction palette, right? You understand? My screen don't stop this. Huh? Well, we don't teach it last class. We have enough stuff that we teach. And that's why this is advanced PLC. So what we're trying to do is show y'all other things besides we have time for, like the move instruction. We use it once in there. And then here, in fact, we never use it in a lab, right? You understand that? But we do it once in here. So we can come up here and put some more runs in there, right? I don't know how many we need, but we can also delete them. Another thing that we're going to require for this lab is we want y'all to get used to. In PLC 1, we called it a master stop switch, right? Well, we very seldom use that because normally we don't use switches, number one, out in industry. We use a lot of push buttons. So every lab that we're going to do, we're going to use what we call a master stop station. So what we'll do with that is we'll come up here and set up this guy right here. I don't know why I'm not using my palettes, guys. I guess because these are convenient. So this is a standard. By the way, over in Germany, and it works the same way. I don't know what they put their stop right over here, but it's the same thing, right? You understand that? And I couldn't get anybody to tell me why I did that. So this right here we'll call this guy input, and we'll use 0/0. We'll call it the start. And we'll call this, we'll use this input 0/0/1. And we'll call this the stop. And then we'll call this the run or whatever you want to call it. I want to do that. Let's see if it works. See if it works. It might. I don't think it will. This guy, we're going to use one of our internal relays because we don't want to sacrifice if this works. No, it's not. Now we can come over here and delete this and call it run. No, it didn't work. I messed up. So what do I need to do? Go down here to symbols. And I don't see it in there again. Well, let's just enter the address. I did something wrong, but we can take care of it. So, and we talked about this. So, what happens when we start entering D3? This little box pops up, and what does it show? Next is available address. Right? You can just go down and click on that if you want to, but we don't want to do that. So this is a standard start-stop station, right? Okay. And then what can we do with that? Now what you got to understand, this guy here is supposed to stop everything. So I had problems last time I taught it. They'd put this at the stop, at the start, and it would mean nothing to the rest of the program. Okay. So how can we disable everything when I hit that? Well, one way we could do it is we could just put one of these in all our rungs, right?
Yeah.
Okay. Another way we could do it, if we were running off the counters, we could also maybe reset the counter. So once we set up a symbol, what can we do from then on? Instead of remembering the address, we can just type in the symbol. Okay, so we got two types of counters. What's our two types of counters? Yeah, count up and count down. So here's our up counter. Oops. Here's our up counter. I'll get it in there. Yeah. Here's up. That's small, guys. That's the only thing I don't like about it. It's real small. Here's our down counter. And then somewhere down the line, we got to have a what? Yeah, reset. So it looks like we got one too many rungs. And by the way, when you drag them, you need to drag them toward the bottom. So when you highlight it, drag it toward the bottom. Because a lot of times if you drag it toward the top, it'll open up your symbol thing and your address thing. So you need to be careful about that. Can't do anything with those right now because what haven't I done yet? Okay. So we'll call this counter, let's use one of these other registers to see if it works. We'll call this C9 and then we'll call this 0. And we'll call this C10 0. I didn't label this. Okay. So preset, we can either, here we're going to address them. So this is an up counter. So if we want to count to 10, then I would put what in there? I put 10. On this one, this is a down counter. If I wanted to count down from 10, then I'd have to put that where? Accumulator, right? Everybody okay? And what do we need to put? No, we're counting from down from. We'll see what's going to happen. Okay, we'll get our palette down. We'll check, see if it's going to compile okay. Don't like this. So what happens if we don't have something quite right? If it's not an error, then this window, little pop-up window comes up, and then it tells us where our error is at, right? Understand? It tells us which rung it's in, and it tells us what the error is. So it says our operand is not entered. Actually, it's not an operand here. It's actually it's an address. If I can enter. Yeah, we should be able to do this too, right? And the counter 1. What's nice about using symbol names is now you're dealing with names and you're not dealing with numbers. Huh? Yeah, thank you. Now, if I was to check the error, it would probably say the error is okay. So all this is doing is checking syntax, right? It doesn't mean you didn't enter it. It don't mean it's right. It just means it's in the right syntax, right? Everything's in there like it's supposed to. You tell me that too. Well, it checked okay. So why didn't it? Oh, it didn't change.
You have to erase it.
I know that'll work, but there should be another way. That's okay. Okay. So here's our master start stop. We're here using both these are what? Examines closed, right. So they're true when they're closed. So here's my stop. I'm going to turn that on. Turn it on and leave it on, right? And then, of course, notice I can't. Of course, what did I leave out, guys? This is what you get when you get in a hurry, right? I didn't give anything to count. So we'll assign this to input flash 2. We'll assign this to input flash 3. Okay, so when I hit the stop, it's another problem we got. Y'all glad y'all see me have, y'all glad y'all see me have problems, right? Huh? Yeah, we'll see. If it don't work, then that's fine. So what was going to happen is it was going to reset when I enabled my master start stop, right? We want it to be able, we want it to automatically reset the counter when I hit the stop button. What we're trying to do. Okay, start. We're just gonna momentary contact, right? Okay, it seals itself in. Now this contact went false, right? Because we got to examine if it's open there. So we're gonna make it count. Here's our first one. It's switch 2. And then when it counts up to 10, it should have what? What happened to my preset? And you're right. So as soon as I got up to 10, it went to what? What? How do we know it's done?
It went on.
Yeah.
I think you can change your preset.
You might be able to change them in program mode, but I don't know if you can change them in run mode or not. Because the thing's actually active. We can try it. I did it. Thank you. I know it wouldn't let me change my counters while ago because I did try it. No, my move instruction. It wouldn't let me change my move instruction. And then it says done, and then what does it keep doing? Keeps counting, right? Okay. And then here's our minus, our down counter. So there's 10, and it's still not 1. So notice the down counter, the done bit is done as soon as you start, right? Okay. And then you have to go what? Past, 1 pass, right? How many of y'all got that on the test? And then the done goes false. So if we was looking at the down counter when it was done, we would use a normally closed contact, right? You know what I'm saying? If we're looking for when the up down count is done, we'd use a normally open contact. So they are not the same. Everybody okay? And we load the what on this guy? Preset. If we use the move instruction, we could load the accumulator with a positive number, but you can't reset it. If you reset it, it would go wrong. It would go to 0. But we could load the accumulator with a positive number, and then it would count down towards 0. All right, you understand that? But you can't do it with a reset. What you have to do is when you reset it, you have to load it. So I think our first lab, guys, is we're going to combine numbers and we're going to combine counters. So let's go ahead and take a break. 10 minutes.
Yeah, we did 9.
Yeah. And unfortunately, Tyler, so from now on, they're not going to give you the dirt diagrams or anything. They're going to give you what we want it to do.
Hey,
So,
that gives you some freedom.
well, it does, and that's what I was telling you. So there should be, if we've got so many groups in here, then everybody should come up with a different way to do it, right? You understand that? So what does it say?